next chapter in operating system, that is the deadlocks chapter. So we understood what is deadlocks and what are the different aspects of deadlocks. Now let's revise once again what are these aspects that we have seen in the last lecture and continue the session with the next section on deadlocks. So we understood that deadlocks is a situation wherein a process is blocking the entire system. That's a deadlock. So if you have n processes that are executing in the system and each process is waiting for another process which is also in a waiting state for some event for that process to make some action, to take some action, then there will be such a situation where all processes cannot execute and finish. They will be in a halt position. They will be in stopped or paused position, and nobody can remove these processes out of this paused position. So that kind of a situation is called as a deadlock. So here we have an example that two processes are there, P0 and P1. Both are waiting for each other. P0 is holding a resource A and P1 wants that resource. P1 is holding a resource P and it wants the resource that is held by P0. So in this way, both are waiting for each other. Since both are waiting for each other, there is a deadlock situation. These both will not be able to finish the execution because they both are holding one resource and they are wanting the resource that is held by another. So that's why these processes will not be able to execute and complete their execution because they are in deadlock state. So this we also understood with an image of moving cars. So if there is a set of cars and there is a single bridge which they have to cross, the bridge is a small place and hence two cars cannot simultaneously go in opposite direction. So what happens is they both come and collide and stop on the bridge. If anyone takes the car back, then only the other cars will be able to move. So that is what we saw, and deadlocks is what we have, it is there, it provides starvation, it can provide it is only possible to avoid the deadlock by preempting resources and rollback. So we will see all these in our today's lecture. So what are the necessary conditions for deadlock to occur? If there is any of these four necessary conditions are present in the system, then there is a possibility of the processes going into deadlock. What are those? First one is mutual exclusion. If all processes are able to hold a resource without sharing it with somebody else, then it becomes a deadlock situation. It will be holding a resource which other process also requires, then there can be a situation of deadlock. Not all resources are shareable. Only some resources are shareable, like your hard disk. You can share the hard disk. One process may be writing to one part of the memory and other process may be writing to another address in the memory of a disk. So there is shareable. Even RAM. Multiple processes are there in the RAM, so that is shareable. Your CPU processor is shareable. Multiple processes are using turn by turn the resource. Excuse me. Hold and wait. Supposing there is a process which is holding a resource R1 and it is requesting for another resource R2. Then it means that it is holding one resource and it is waiting for another resource. That's what is hold and wait. If there is a hold and wait situation, what will happen? Supposing if process P1 is holding a resource R1 and it is requesting for another resource R2 which is held by a process P2 and that is also in waiting state, then what happens? Previously we saw P0 and P1, they were both waiting for each other to release the resource that the other one was having. So that is what is hold and wait. It is holding a resource and it is waiting for another resource. No preemption. When a process is holding a resource and that resource cannot be preempted, means it cannot be taken back from that process, if it is in the waiting state, then that is called as another situation that can cause a deadlock. So no preemption. The processes which are holding the resources, they hold the resource until unless they don't finish the execution. Actually, if they are put into waiting, we can take the resources back if possible. Some of them can be released and again reallocated, but Here some resources cannot be reallotted, they cannot be restored, and hence there can be an issue there. So the processes will hold the resource until the end of the execution, and if they are in halt position, then they can halt others as well, and that can cause a deadlock. Next one is circular wait. I have explained your circular wait that P1 is waiting for P2, P2 is waiting for P3, P3 is waiting for P4, and P4 is waiting for P1 back. So if there is a circle of waiting, then it is a deadlock situation. Next we saw resource allocation graph. So what is a resource allocation graph? It's a graph that represents what resources are allocated and what resources the process are requesting. So you can have process set defined as P1 to Pn, and we can have a set of resources R1 to Rm. These resources can have n instances. One resource can be in n number. Like for example, you have a quad-core processor, then how many CPUs are present in your system? 4 instances. CPU is 1, but there are 4 instances of CPU on your system. So that is what is called as an instance. Resource and instance. Resource is 1, instances are n number. So you may be having RAM, which is more than 1 RAM in your system, then that is 2 instances of RAM are present on your system. So that is what is instance. So here in a resource allocation graph, we use 2 edges. One is a request edge and second one is a assignment edge. A request edge is when a process wants to use a resource, then it will have a request edge. So that process is requesting to allocate a resource from the system. So that is a resource request edge. What's an assignment edge? Assignment edge means the resource is allocated to a process, then it becomes an assignment edge. So let's see this in diagrammatical representation. The process is represented using a circle. Resource is represented using a rectangular box with instances indicated by dots in them or by a square box inside the rectangular box. And then we have request edge. A request edge is process to resource this direction. If the edge in arrow is towards the resource, that means it's a request edge. If the arrow is towards the process, it means that this resource is allocated to this process. So which is the in angle, that will indicate whether it is a request edge or a assignment edge. This is a graph which represents the number of processes and the number of resources that are there in the system, how many instances they are, and who is holding which resource and who is requesting which resource. So if you see this graph, yesterday we have discussed this. So you all already know that resource R2 is having 2 instances. R1 on the other hand has single instance. R3 has single instance. There are 3 processes P1, P2, P3, and we have R4 which is having 3 instances. Now which resource is allocated to which process? From R2. From R2, one instance of R2 is assigned to P1 and another instance of R2 is assigned to P2. P1 has requested R1 resource and R1 instance is allocated to P2. P2 is requesting R3 and R3 is allocated to P3. So this is the resource allocation graph. So how will you identify whether there is a deadlock in this? Yes. If there is a cycle, that means there is a deadlock. So yesterday we understood that if there exists a cycle, there is a possibility that a deadlock can occur. So in this case, yes, there is a cycle, but the cycle, this is not necessary that it will cause a deadlock. Why? Because if you see, sorry, we don't have a cycle here. Because R2, from R2 we can go to P1, from P1 we go to R1, from R1 we come to P2, but from P2 we don't come back to R2. Right? So from P2 we are going to R3 and from R3 we are going to P3. There is no cycle. So hence there is no deadlock in this graph. Let's see another example. So here is there a deadlock? Yes, yesterday we have discussed this and we saw that there is a deadlock. So from R2 we go to P1, P1 to R1, R1 is allocated to P2, P2 is requesting R3, R3 is requesting assigned to P3, P3 is requesting R2, and hence there is a cycle here. Because there is a cycle, then obviously there is a deadlock situation. This is another diagram that represents the cycle, but there is the possibility of deadlock is not there here. Why is that? See, here there is a cycle from R2 P1, from P1 R1, from R1 there is an arrow to P3, from P3 there is an arrow to R2. There is a cycle. But if you see, one instance of P1 is assigned to P4 and another instance of R1 is assigned to P2. Since these two are independent processes, they can finish their execution and release this resource, which can be given to those processes which are in that cycle, and hence we can break this cycle. So it means that if there is a single instance of a resource, there can be a possibility that there is a deadlock if there is a circular wait, if there is a cycle in the graph. If there are multiple instances, then there is a possibility that there will be no deadlock if there is a cycle also. Even though there is a cycle, there is no there can be a possibility that there is no deadlock. It cannot have a deadlock because there are independent instances, multiple instances of a resource, and that deadlock avoidance can be taken care. So what are the basic facts? The basic facts are that if graph contains no cycle, there is no deadlock. If the graph contains a cycle, then there are two situations. Either there can be a deadlock or there cannot be a deadlock. If there is a single instance of a resource, there can be a deadlock. If there are multiple instances of a resource, then the possibility of deadlock reduces. Next, methods for handling deadlocks. So what are the methods for handling deadlock? You should ensure that the system will never enter into a deadlock state. Then you have two options. One is deadlock prevention. Second one is deadlock avoidance. These two algorithms, there are algorithms that will help you all to prevent deadlock, and there are algorithms for avoidance of deadlock. Then most of the systems allow the system, you all can do what? You all can allow the system to go into a deadlock, and then you all can recover from the deadlock. That also option is available. But most of the systems ignore the problem and pretend that the deadlocks never occur, and they keep the systems going on as they are executing. Most of the operating system, including Unix, follows this policy. They assume that deadlock will never happen and they will execute, because most of the processes are processes that execute quickly and release the resources, and hence these systems will not have a chances of deadlock. So next we will understand deadlock prevention. So how you all can do deadlock prevention? Deadlock prevention can be achieved if you all try and take care that 4 necessary conditions for deadlock to occur are not happening. If you all take care that these situation does not arise. Which are those necessary conditions for deadlock to occur? First one is mutual exclusion, second one is hold and wait, third one is no preemption, fourth one is circular wait. So if these 4 situations you all take care that it doesn't happen, that means no mutual exclusion. You will allow the resources to be shared among the processes. Then there is no deadlock. Second, you will take care that the processes should not hold and wait for another process or resource. They should not request for a fresh resource when they are already holding some resource. So that is second option. Second necessary condition that has to be taken care. Third necessary condition is no preemption. If the process has some resources held with it, then you should be able to preempt it. Means take back those resources from that process, and then you all will prevent the deadlock. Next, circular wait. Take care that the process do not go into a circular wait. One process does not wait for another process. That process waits for another process, and the last but one process waits for the first process. If you take care that the cycle doesn't occur in the system, then there will be deadlock prevention. But how will you all do all this? And is it possible to do this? Next, What are the disadvantages if you all take care of if you all make such policies where these necessary conditions do not satisfy? So if you all take care that these necessary conditions do not satisfy, then there will be some compromise on the other end, like throughput and resource utilization. You all can reduce the resource utilization of such systems. That is also a waste of the resources. So let's see each of them how we can do it and what are the disadvantages of them. First one, mutual exclusion. First of all, you all need to understand that not all resources can be shared among multiple processes. Your RAM is shared. How do you say RAM is shared? In the RAM, you have operating system loaded here. Then you have process P1, process P2, process P3, all loaded in the RAM. So this is a single resource in the system, RAM, and that RAM is shared by different processes. So all of them are using the RAM. The process can be removed and the new process can be added into the RAM. While one process is getting executed, another process the OS can bring in the process into the RAM and remove the process from RAM due to several reasons. So this is a shareable resource. But is your printer shareable? Is your monitor shareable? Can you see multiple things on the monitor simultaneously? If it is a full screen, of course we can see multiple windows on our monitor, but can you interact with all the programs simultaneously? No, you can interact with only one program at a time on the monitor. So the monitor is not shareable. If it is non-shareable, one process only gets the monitor attention at a time, not multiple monitors attention at a time. Similarly, your printer can print only one document at a time. It cannot print two documents together simultaneously, right? Only one. So if the printer is printing one document, the other document has to be in the queue. It will be waiting in the queue. When this printing is over, then only the next print order will be taken by the printer. So that is what is non-shareable. So if there are shareable resource, of course you can share them, but if you have non-shareable resource, then it is difficult to prevent deadlocks by defining a mutual exclusion condition for this. Next, hold and wait. Guarantee that when a process requests a resource, it does not hold any other resource. So what you all will have to do is, you all will have to make a policy that at the beginning only, let that process tell how many resources it requires. All the resources that it requires will be allocated once only. Right? So it will not hold and wait for another one. So initially only we'll give you to whatever it requires. You tell me what all you require, I will give you all the resource and start the work. Okay? So what happens here? It will cause the wastage of resource utilization. It will not have the efficient utilization of the resources. Why? Because supposing if there is a process P1 which has the following task to do. It needs to copy from your pen drive. Okay? From your pen drive it has to copy one document. This is a pen drive. And it has to copy it to your disk. So first thing that it is doing is it is copying. After it finishes copy, you are going to print that document. Right? So this is the order in which it has to do. So this is open the tape drive first, acquire the tape drive first, acquire the disk second, copy all the content, and third, request for a print of the document. So in this way, if you are giving these resources, all the three resources to process P1 at the beginning of its execution, what will happen? First of all, it will have to open this tape drive or a pen drive, copy that file from here to this location in the disk. Then this process, as this process is going on, the printer has nothing to do. It is simply sitting and waiting for the order to be printed. This means that the printer is in waste. Okay, finish. This copying gets over. After the copying gets over, the printing starts. What about this pen drive? This pen drive is allocated to process P1, no other process can use it because we said that we will allocate all the resources to a process and wait until unless it doesn't finish and it releases the resources, we are not going to use the resources. So what is happening? The pen drive is unutilized because there is only printing happening now. That also printing, you send the document to the printer, the disk also is not needed. The document will be copied on the printer, it will be in the queue and it will print from there. It doesn't require the disk to be present. So both these resources are not utilized because the printer work is going on. Process P1 has not finished its execution. So it will not release these two devices. So only it will release these two devices when all three activities are done. Right? So that is one task, one thing that you all can do. You all can take care that all resources are allocated to the process at the beginning and then when it finishes it will release all those resources. So that is how you all can take care that the hold and wait does not occur. Alternatively, what you all can do is request resources only when it has none. So you can take care that it can request a resource only when it has none. So if it has taken the pen drive, then it should release the pen drive, then only it can request the disk. If it finishes with the disk work, release it, then only request for the printer. So in this way, the processing will be again complicated. It will reduce the efficiency of the system. Next one is no preemption. How will you avoid no preemption? Means you all will have to take back the resource from the process who is in waiting. So what you all will do? If a requested resource can be immediately granted, preempt all resources allocated. If you have a process is requesting for a resource and that resource is available, you all will allocate it. If that process is requesting a resource which is held by another process and that process is not executing, it's on wait, then best is you take that resource and allocate it to this process, let it finish execution. When it finishes execution, then you all can give that resource to the other process. Next, what you all can do? Preempt resources from waiting processes if the request by another process. So if the request is, if that process is resource is already available with the operating system, it will provide the resource and it can execute. But if that resource is is available with some other waiting process, then it's better to preempt it, take it back and allocate to this process. So what is the problem? The problem here is that the other process may be in halfway in doing some work and it has done halfway and it has to redo the entire process, entire task. So that is a difficult thing here. So the protocol applied if process state can be saved and restored. So if you can save and restore whatever half thing that it has done, then it is better to preempt it. Otherwise, it is not a good idea to preempt it. Next is circular wait. How will you avoid circular wait? If you want to avoid circular wait, what you all need to do is make a list of all the resources and the resources that is required by a particular process and then give it enumeration. Now, for example, in my example, I said there is a pen drive and then there is a disk and then there is a printer that is required. So what we will do is we will allocate the pen drive as enumeration 1. Disk as 5 and printer as 12, and we will tell that the process can only request resources which are of higher enumeration, not of lower enumeration. Okay, so that is how we will take care that it does not go into circular wait. So in that case, how this will work? Supposing P1, all these resources are given enumeration number. So P1 makes a request for the first one, F1, F of tape drive, which is equals to 1, enumeration is 1. So then it will only can make request to either printer or disk, which are of higher enumeration. Once it makes a request for disk and it releases tape drive, it cannot make a request back to tape drive, because it has already taken a resource which is of higher enumeration. So in this way, what will happen is, if process P1 is task and it releases it, then P2 process can acquire the tape drive. P2 can acquire the tape drive. So in this way, we can take care that there is no circular wait. Deadlock avoidance. Another way of doing this is deadlock. Prevent deadlock because disadvantage. It will affect the throughput and it will affect the resource utilization. So what you all can do is you all can go for deadlock avoidance. So how to do deadlock avoidance? The deadlock avoidance requires some additional information about resource requests and resource allocations. So what all it will require? It will first need to understand how many resources are already allocated to the process. It will next require, it will also require to know how many resources are available with the operating system. First, for the process, any process in the system, how many resources are allocated to it? How many resources are allocated to the process? Next one, operating system has how many resources? The resources that are there in the system that is available. How many resources are available with the operating system? How many resources are allocated? So this is allocated. This is available. And then you will have what will be the future need. First, you need to understand what is allocated. Next, you need to understand what is available. And third, you will require to know what these processes will request in future. How many resources it may require in future. So, if you all know these, then there is a possibility that you all can avoid deadlock. You all can smartly analyze what is this. There are different processes P1 to so on till Pn. If there are n processes in the system, each of those processes, what is the resources allocated? What are the available after all the allocation? How many resources are remaining? And each of these processes require what resources? And how you all will be able to allocate this resource. Excuse me. Information so that we can make a algorithm so that we efficiently allocate resources and we can take care that the deadlock is avoided. So a deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that a circular wait condition never exists. So this is, and if an algorithm is taking care that the circular wait never exists, avoidance algorithm. So a resource allocation state is defined by the number of available and allocated resources and the maximum demand of the processes. So you need a resource allocation state. So this state can be a safe state or an unsafe state. What is a safe state now? A safe state is a state where you can allocate the resources to all the processes without deadlock occurrence. And what is an unsafe state? Unsafe state is a state where a deadlock can occur. So if there is a processes wherein they will go into a circular wait and they will block all the processes on the system, then it is called as a deadlock. And that state is called as an unsafe state. So a state is safe if the system calls can allocate resources to each process in some other and still avoid a deadlock. It can allocate each process whatever request it makes and avoid a deadlock. So that is called as a safe state. And the sequence of the processes in which they will execute, so like here we have written P1, P2, so on till Pn, but not necessary that they will execute in that sequence. Whatever sequence they execute, such that they don't go into a deadlock state. That is called as a safe sequence. So is a safe sequence for the current allocation state if for each PI the resource request that PI can still make and can be satisfied by the current available resources plus the resources held by all Pj with j less than I. Means whatever allocations are already done to the n processes, if one process makes an additional request, if you are able to allocate that resource without making the entire system to go into a deadlock, is called as a safe state and a safe sequence. So we will understand this with algorithm. The first algorithm is a resource allocation graph algorithm. So you all have already understood that resource allocation graph has a edge, which is allocated edge, and we have a request edge. With these two edges, we have an additional edge, which is a dotted edge. This dotted edge indicates a claim edge. What is a claim edge? An edge wherein a process may request the resource. A process may request in future that resource. A solid line indicates that this process, this process P2, the solid line here to this resource indicates that this process has already made a request to R1. Whereas this dotted line indicates that in future P1 will request R2 and P2 will request R2. P1 and P2 may both request R2 resource. So this is a claim edge. A claim edge is always denoted using a dotted line. So what you all will get to know from this, and how will you all be able to avoid a deadlock? You all can avoid a deadlock by seeing this graph, that if I allocate a resource R2 to the process P2, then this system will go into a deadlock. Why? Because R1 is allocated to P1, P1 is requesting R2, but R2 is allocated to P2 and P2 is requesting R1. So there is a circular way. So that's why this will go into a deadlock. But if I take care that when P1 requests, I will allocate P1 the resource first because it is already holding one resource, then it will finish its execution, then P2 will go to get both the resources. So we are avoiding the deadlock. So this kind of a claim edge will help us understand whether there can be a cycle in the graph, and if we avoid happening such a cycle in the system, then there will be no deadlock. So here there is a graph. So this graph here shows that whatever I have told you, that only. This is an unsafe state. That's what I told you. If R2 is allocated to P2, then this entire system, the two processes will go into a deadlock situation because R2 is held by P2, P2 is requesting R1, R1 is held by P1, P1 is requesting R2. So neither P1 will be able to finish, neither P2 will be able to finish. But instead, if we had allocated R2 to P1, then P1 would have finished its execution, then both R1 and R2 could be allocated to P2 after that. Right? So that would avoid our deadlock. Next is the banker's algorithm. So what is a banker's algorithm now? A banker's algorithm is an algorithm that will help us to detect that whether the sequence, the state is a safe state or is an unsafe state. It's a method of, if we have a number of resources allocated to a process, how many it requires totally and how many are available with the operating system, we can take care that which resource has to be allocated to which process, at what state, at what sequence these processes should finish their execution. Then we can avoid the deadlock. So let's understand what are the data structures needed for this algorithm. The first one is the data structure available. Available is an array, is a vector which tells us the number of resources that are required, that are available with the operating system. A vector of length m indicates the number of available resources of each type. If available of I equals k, that is, there are k instances of a resource type Rj available. So this is what we are talking about, the available resources with the operating system. Like for example, on your system, if I say CPU, there are 4 instances of CPU, or if it's an octa core, then 8 instances of CPU. Supposing if I say there are USB drives. There are 3 USB drives on your system. So this is available. So operating system has 8 CPUs and 3 USB drives. Okay. Next, max. Max is an n by n matrix. Max indicates processes on one side, P1, P2, P3, so on, and on another side it indicates the resources R1 and R2. Supposing these 2 resources, P1 requires 1 CPU, 1 USB, P2 requires 2 USBs and 0 USBs, then P3 requires 1, I'll take only C3, okay, and it requires 1 USB. So what is the requirement? P1 requires 1 CPU, resource R1 is CPU for example, and R2 is USB. Processes, the first process requires 1 USB, 1 CPU for execution, and it requires 1 USB port. P2 requires 2 CPUs, but it does not require any USB port. P3 requires 1 CPU and 1 USB port. So it is an M by N matrix where it is M and N indicates the number of processes and number of resources that are available in the system. So an N by M matrix defines the maximum demand of each process, total how much it requires. If max of ij equals k, if max of I and j is equals to k, it means that it requires k instances of resource R. So then Pi may request at most k instances of resource type Rj. So I indicates processes and j indicates resources. So if there is k value in the max of ij, in this max of m into n, then whatever is this value 2, this 2 indicates that process P2 requires 2 instances of CPU. So this is I and this is j. So it is max of ij. If it is equals to k is here 2. It means that ith process requires jth resource of 2 instances. Next one is allocation. Allocation means it indicates how many resources are already given to the process. So allocation. Allocation also is a m by n matrix. Here again n by m. So here again we have processes P1, P2, P3. So that is maximum that is the resource required. This is R1, R2. R1 is CPU and R2 is USB ports. Okay. So supposing you have allocated it okay, we will make it 0 and we'll make it 1. What does it mean? P1 has been allocated 1 USB port but not allocated till the CPU. Means what? It has got USB but it has not got the CPU to execute its program. It has not got the CPU for execution. Supposing there 1, here 0 and here 1, here 0. What is max available with us? 8 CPUs and 3 USBs, right? So out of that, how many are already in use? Already in use are 1 USB is in use. Then CPU, 2 CPUs are in use. So totally how many are available with the system now? 2 minus 8 is 6 and 3 minus 1 is 2. So available are only 6 and 2. Totally there are 8 and 3. But out of that, this is what is already utilized. Okay. Next is need. What is need matrix? What is the maximum requirement and what is already allocated? If you differentiate that, you all will come to know how many resources are all required by these processes. So let's calculate the need matrix. So I will do it here only so that you all will be able to say it. Need. P1, P2, P3 and resources R1 and R2. Okay. P1 requires 1 CPU and it has got no CPU now. So you need one. It requires one USB and it is allocated one USB. So 1 minus 1 is 0. So in future it is not going to ask you any USB port because you have already given it the USB port that it requires. Next one, P2. P2 requires, max it requires two CPUs and you have already allocated it one. So in future it will ask you one more CPU. And USB ports, it does not require any USB ports, so 0. Next one is P3. P3 requires one CPU. You have already allocated one CPU, so 1 minus 1, 0. And USB ports, it requires one. You have not allocated anything, so 1. So this is need, and this is allocated. So it indicates how much maximum it will require in the entire life cycle of that process. From the beginning of execution till the end of the execution, how much resources it will utilize. Next is need matrix. It is how much you have, after allocating whatever minimum you have allocated, what is it that it will ask for in future based on the maximum that said that it will require. And allocation is, it tells you that the number of resources that you have already given. And available will always be dynamic because it is what the operating is holding with it to allocate to all the processes. So that is the various data structures that we require for Banker's algorithm. Now let's see the algorithm. So this is the algorithm, safety algorithm. So first we have to check for the safety algorithm, then we have to do the allocation. So there are two algorithms, and while solving the problems you will have to apply these algorithms and check and do the allocation. So let's understand this. The first statement says let work and finish be vectors of length m and n. There is work vector and there is finish vector respectively. Initialize work is equals to available and finish of I is equals to false for I is equal to 0 to n minus 1. What is this? Work indicates how many how many resources we have at hand and how many we will be at hand we have at any point of time in the entire life cycle of and all these processes to finish its execution. And finish indicates which process has finished the execution. Next one is find an I such that both finish of I is equal to false and need of I is less than work. So we have, this is the need 1 and 0. Okay, let me just rewrite it once again. So this is the max and allocation. Okay? So we have work. Work is equal to available. So how many are allocated? We have to remove that from the available. How many are allocated? Total 6 are remaining. 1 is okay. So our work is finish is equals to false initially. So it is the sequence, stage sequence in which the process, all these three processes finish execution without having an hurdle. Okay. Next, what do we have? Finish of I is equal to false. So finish of P1 is false, finish of P2 is false, finish of P3 is false. All three processes have not finished. They are still in execution. So their finish is false. Next one. Need of I is less than work. Need of I, work is 6 and we have as many requirements of the processes is there, that many resources are available, that many instances of the resources are available with us. So we can safely allocate these resources to the processes and finish their execution. Next one, if no such I exists, go to step 4. If no such process exists, so supposing now we have here, what would happen? Or I had 0 USB, I had only 1 USB, I have allocated it, and it requires, this also requires 2. So 1. So what happens? And this also exists. If CPU USB ports are not available with us enough to allocate of their process the number of instances that it requires, we have to see the need. Based on the need, there must be that many resources. If whatever we require, if they are not available with us, then we cannot provide them. Like for example, now I have 0 USB CPUs, or there is 1 CPU and there is 0 USB. So in that case, this requires 1 USB, 1 CPU and 1 USB. So it is not possible to allocate it. This requires 1 and this requires 0. Yes. This one can be allocated to P2. P2 can finish its execution. But if P2 required 2, instead of its max requirement was 3. So it becomes 3 now. 3 minus 1, 2. Max it need is 2. But we have only 1. So again cannot. This requires 0 and 1. We cannot, because USB is 0 and it requires 1 USB. So in this case, if you see, there is no safe sequence. Why? None of the process requirements I can satisfy. This requires 1 USB. Yes, I have 1 USB, 1 CPU. It requires 1 CPU. I have 1 CPU. It requires 1 USB, but I don't have any USB with me. So I cannot satisfy this need. So this process cannot finish its execution. Go to the next one. This requires 2 CPUs and I have only 1 CPU. No, I have no USB, but I cannot satisfy its CPU request. So this process also cannot execute. Next one, 0 and 1. Does not require any CPU, but it requires 1 USB. I don't have any USB with me. Whatever I had, I have already given it to process P1. So this also cannot finish its execution. So if there is no such I exists, go to step 4. If finish of I is equal to true for all I, then the system is in a safe state. But none of the I processes have finished execution. So all of them finish is still false. So it means that this state is an unsafe state. It's a deadlock state. Correct? But if I this is, and in the same situation, if you see, what will happen now? Which process can finish its execution? It requires 1 0. I have 1 0. So I can allocate P2 the resource. So P2 will finish first. P2 finish will become true. Okay. Next one. After this finishes, whatever its max is there, it will return back. So there was 2 plus 1. There is now 3 CPUs and 0 USB. So whom we can allocate it? These 2 cannot be finished. Why? Because 1 it was requiring, it requires 2 and we have 1. It cannot be satisfied. Right? But if I have this 1 USB request, so 1 minus 1, this would be 0. So could I satisfy this now? Yes. because I have 3 CPUs and I don't require any USB. Whatever USB was required, it is provided. So this finishes next. Next, P3. When this finishes, whatever was it will return. Now, this need can be satisfied. That means P3 will. So that means all 3 have finished execution. So the system is in safe state. This is the algorithm. So this algorithm may require m into n square operations to determine whether the system is in safe state. So resource request algorithm. So we have another algorithm, resource request algorithm, to see whether you can satisfy the request. So let request be the request vector for a process Pi. If request of the jth request is equals to k, Pi wants k instances of resource type Rj. Request I, j, I and j is equal to k, then process Pi will require k instances of resource Rj. So if request of I is less than need of I, go to step 2. Otherwise, raise an error condition since the process has exceeded its maximum claim. So if the number of requests is request is less than need, then yes, you can provide it. If request is less than available, go to step 3. Otherwise, Pi must wait since the resources are not available. So if you request whatever amount you are requesting for, it should be first step, number of requests. The request that process is making. I want 5 CPUs. If it is saying I require 5 CPUs and its need says it requires only 2 more, then it is requesting more than its need. So that means that there is something wrong. So you should stop there only. You should raise an error condition and you should quit. You should exit that process. But if it says that it requires 1 process and its need is 2, that means the request that it is making is less than what is its need, then yes, you can go to step 2 and check whether that 1 process that it is requesting, 1 resource that it is requesting is available with the operating system. It is available, then you can allocate it. If it is not available, that process has to wait till that resource becomes available for this process. Okay. So have the system pretend to have allocated the requested resources to process Pi by modifying the state as follows. Available is equal to available minus request. Allocation is equal to allocation plus request. Need is equal to need minus request. So you will have to update this. So we will see this with another example. You can note down this example. Copy this example and we will solve this example in the next class. So you all can calculate what is the need from this max and allocation. So subtract the allocation from max and calculate the need, and we will solve this problem in the next class using the Banker's algorithm, the 2 algorithms that we have seen. One is the allocation algorithm and second one is the safe algorithm. So you will use both these algorithms and solve this problem. This problem can be asked in the exam. It's an always a problem like your CPU scheduling algorithms. This problem also is always present in your question papers. Very important. So you all try and